So the next, this is the difference between the almost all and all. For the continuous case, we need that almost all thing. Now the next theorem is very, very important. It's actually very useful to calculate something. This is like a algebraic calculation. So let xn be a sequence of random variable and x such that xn tends to x in log. That is the distribution function converts to the corresponding distribution function weakly. And let C be any real number, constant, fixed real number. Then what happened? Then there are several things happen. Number one, if we add C, xn plus C, this goes to x plus C. This is trivial, basically, is as n tends to infinity. Now the second case is C into, if you just product multiplied by C, it is just like a C in the sequence of real number also. As n tends to L, the 2 into n tends to 12, like that. So it is 2C into the random corresponding random variable. So it's just the C into the corresponding random variable. Now, this is very weak convergent, very weak concept of convergency. Now, next is a slightly stronger concept of convergency. This is this. So again, let xn be a sequence of random variables. And on the probability space, so omega script A for A, and this probability function is there. We say the sequence converts to, we say that xn converts to x in probability, in P, in sometimes I call in P or just P. P means P for probability. So it is convergent in probability for A as n tends to infinity. What is the convergent probability definition? The definition is like that: for all epsilon positive, is for every epsilon positive, that probability of xn minus x, the difference, greater than epsilon, that probability is goes to 0 as n tends to infinity. Remember, there's a that probability goes to 0. This xn minus for every epsilon, this probability goes to 0. So you can just, this is just a probability. So this is a real number, the sequence of real number. So equivalently, we can say that we can say for every epsilon positive and say for every delta positive, there exists and sequential convergence. This is n0 belongs to the natural number, such that whenever n greater than n0, that probability of this part, this thing greater than epsilon part probability is actually less than delta. Obviously, it's greater than equal to minus delta because greater than minus delta because it's already positive. The probability is positive, so no need of writing the greater than minus delta. It is just less than delta. You can use this thing also. So this is the probability convergent in probability. There are other convergent concepts also. So we have only discussed only two convergency. One is the weak convergent, another is probability convergence. There are other convergence also. We'll go later. So remember, this convergent is the convergent probability of this xn. So It's not just that xn is a function. Remember that xn is a function with some probability thing, and then the distribution function, the PMF or SPDF, or the continuous, these are all functions. And there is a corresponding probability also, and this probability is a sequence of real numbers. So you should distinguish between what is the random variable, what is the functions, and what are the sequence of real numbers. In case of sequence of real number, this is a convergence thing. In case of sequence of function, we need that to say what is the pointwise or this uniformly convergent. And for the sequence of random variable, there are different sequence of convergence: weak convergence, strong convergence, that is convergent law, then convergent almost surely convergent, then convergent probability. This actually is a convergent in some different metrics. Same set, but a different distance concept. So one example be very clear to us what is the probability convergence. So example is this. So consider the xn is such a random variable, sequence of random variables, such that the probability of xn equal to 1 is just 1 by n, and this probability of xn equal to 0 just 1 minus 1. So it is just a Bernoulli. It's a Bernoulli with probability, success probability 1 by n. Now, what is the probability of then xn is bigger than xr? Now, this have two things. So if epsilon is greater than or equal to 1, that is xn greater than or equal to strictly greater than 1, that is 0, obviously. And if epsilon is under between 0 to 1, then what? Then it is just 1 by n. This probability is just 1 when this in 0 to 1. So this is a probability. Now, is this probability goes to 0? Yes, this probability goes to 0. So now this probability goes to 0 as the intention. That means this probability of mod xn greater than epsilon, this goes to 0 as the intention. Therefore, we say this xn goes to 0 in P, just P. So 0 means it is a 0 random variable. So now there is a very important result in this. So different results is this. Number one result, and you can easily verify this, all these things. You have to verify all these things. It is very easy. Some are in book, but some are in just so easy that is left as exercise. So if xn tends to x in probability, this if and only so is implies and implied by xn minus x goes to 0 in probability. The second part is this: if xn tends to x in probability and xn tends to y in probability, it goes to two different random variable, what happens? Then the probability of xn equal to x equal to y is just equal to 1. This probability. So almost all equal. Maybe some point where they are differ, but this probability, or a collection of that set where they differ, this probability is 0. So what is the proof? The proof for proof is this. So the proof is this. So now probability of mod x minus y is greater than c is less than or equal to probability of xn minus x greater than c by 2 plus probability of mod xn minus y greater than c by 2. Now, this probability goes to 0. that xn minus x greater than c by 2, and for the xn greater than minus y, this greater than c by 2 also goes to 0, so this goes to 0. So that means the probability mod of x minus y greater than c goes to 0 is actually 0. So for all c, so this is true for all c. No, for all c, this is true for all c. Since it's true for all c, that means that there cannot be differ. So they can differ with the just a probability 0. The third one is this: if xn goes to x in probability, and that implies actually xn minus xn, that the difference goes to 0 in probability, as mn both tends to not a single thing, you have to go both index run 0. The fourth one is this proof is similar. This proof is similar to the 2. The fourth one is the xn in probability goes to x goes in probability, yn goes to y in probability, then that xn plus yn goes to x plus y in probability, and xn minus yn also the difference, not the difference, is xn minus y goes to x minus y in probability. So this is, it's like a real number thing, real sequence, same as the real sequence. Similar, the 5 is same as the real sequence. Like if xn goes to x in p, and some k is some constant, say c is some constant, c is some real number, then what happens? Then c into xn, c into xn tends to converge to, in probability convergence, c into x. So these are like real sequence. The sixth one is this: if xn goes to x in probability, then xn square, that random variable, transform random variable, goes to x square in probability. Oh, again, it just tends to in. So for the seventh one is slightly tough, that if xn goes to x in probability and yn tends to, sorry, it's a. Next we go to the just a single constant thing a, and y goes to b, ab are constant, ab are real, then this implies that xn yn goes to ab in probability. And this you can use this, it is easy if you use this. The proof is like that. You have to use this identity xn yn. You know, 4ab is just a plus b whole square minus a minus b whole square. You have to use this inequality, this relation. And we already proved that xn plus yn goes to a plus b, and xn minus yn goes to a minus b. So done. This proof is easy. So you have to just use the very simple school level identity. The eighth one is this. This is slightly tough. If xn goes to, say, 1 in p, then this implies 1 by xn tends to 1 in probability. And given that that probability of xn equal to 0 is 0, otherwise there is a problem. You can't take the 1 by xn. So that's why we need that probability of xn equal to 0 is just 0. Xn can be 0, but that probability is 0. Now this proof is slightly complicated. This is actually the other easy. This is complicated. So what is this? What is the line of proof? The proof is like that. The probability of 1 by xn minus 1 is greater than equal to epsilon. This is nothing but probability of 1 by xn greater than equal to 1 plus epsilon plus probability of 1 by xn less than equal to 1 minus epsilon. Now this probability of 1 by xn getting 1 plus epsilon plus probability of 1 by xn. Now we choose epsilon is small, so this is less than equal to 0. Plus this part, that part so if sorry, if you choose epsilon is very high value, then this will be 0. But if you choose epsilon is small, then this is not 0. So epsilon is small, so it is that part is important from 0 to 1 minus epsilon. So we break this whole interval 3 parts. One part is greater than equal to 1 plus epsilon, another part is less than equal to 0, another part is 0 to 1 minus epsilon. Now what is this? This is nothing but probability of probability of 1 by xn greater than equal to 1 plus epsilon plus now each part is goes to 0 actually. No need of doing this. Now each part is goes to 0. Actually, the every part is portion is goes to 0 because as n tends to infinity, we have this xn tends to 1. So since xn tends to 1, that first part is goes to 0. Now since xn tends to 1, so that means it can't be non-negative. It's be positive for large n. And that probability must be goes to 0. That can be probably negative, but that probability will goes to 0. Since xn goes to 1. The third part, the important part is the third part. What about this 1 minus xn? Is again similar. So 1 minus 1 by x, not so 1 minus 1 by xn less than equal to 1 minus epsilon is nothing but xn greater than 1 by 1 minus epsilon. So which is away from 1. So that's why this part goes to 0. So all this part goes to 0. So this tends to 0 as n tends to 0. The ninth one is this xn goes to a in probability and yn goes to b in probability. A, B are constant, obviously A, B are real number and b not equal to 0. Then xn by yn, so xn into yn to the power minus 1 goes to a by b. That's why it takes b not equal to 0 in probability. So everything in probability. The 10th result is this. Now we have this important result. So xn goes to x in P and y is a random variable. This implies xn into y goes to x into y in probability. The 11th result is this. That xn, if xn goes to x in P and yn goes to y in P, then this product xn yn goes to P, goes to xy in probability. And obviously this if xn goes to x, then xn square, xn goes to x in P. This implies xn square or xn cube goes to x square, sorry, in P, in x square. So these are some results, and using this result we prove some important theorems in convergence of in probability or convergence in distribution. The proof of this result, some are easy. The last 3, 4, that are 7, 8, and this 10 is slightly complicated, and this 10th one is the most complicated. I'll prove in the next lecture. In the meantime, you just try to attempt the proof of all this easy part, and then try to attempt this part also. That 11 is the not the 11, the 10. The proof of the 10 is the most typical one, the top one. I'll prove in the next class. The rest thing you should do yourself.